Okay, so the record is on. Let me state again that even though the content today is pretty much like the concept, but it is the most important thing. You must see that you understand the concept to get through things right. So it's you know, a tiny number of students still get messed up when you are asked to design. You don't know what to compare. You know, the demand and supply side of things. You know, you may call that the load and resistance, as the RFD suggests. That is also the right way to call it. Okay, the right here, the keyword, load and resistance. Okay, now you have known the concept of the nominal and design strength. That's another very important aspect of the design. Okay, so let's come back here. Now you know the material that you're going to use based on this. Now it's a standard. You see, right here, it's a TIS. It's a Thailand industrial standard. Things like that. It says that, okay, your materials rather have to meet these numbers. Okay, and we are talking about that. So now, because one thing that you need to know is that we use manufactured products. That means all the steel sections are manufactured from the factory. All the sizes and things are available to us from the beginning, unlike the steel that you can create any size or shape to your liking. But that would mean that you start really from zero, because you have to try your section. But for steel, we already have the sections manufactured based on TIS. So now it's time to get to know the shape. Okay. In this class, predominantly, we are going to use this one. It's a basic standard shape that we call Y flange. So I think it's a good time to say know what it is about a little bit. Let me try to go back to the first page. I always forget this. I think I can move this later on. Okay, so you know, it looks like this. Okay, I deliberately try to draw the top part thicker than this, you know, part. Okay, this big part is called flange. All right. Thai word, they use the word peak. Okay, wing. I don't know. It's flange. Okay, and you know, when in mechanical engineering stuff, when you try to connect two tubes, the way to connect the tubes, they use stuff like this. Okay, they put the thick plate in the end to connect the tube. You can look at the tubes. It's just some, you know, lying around our building as well, you know, near the tools engineering department, and then they bolt them together. This is also called flange, but in Thai word they call this na plan. So you know, when the first time I came across that word, I was just, what the heck is that? So anyway, in English they call flange. Again, it's really easy to understand. This part is called web. In Thai language, they call it eo. Okay, so yeah, here we go. There's a little curve here due to the manufacturing process. Now, according to TIS, all the steel made in this country, this is part of a circle. You can call it a quarter circle. Okay, and therefore there is a radius. This is R, and this portion is called fillet. Okay, if I am going to draw it bigger, it's going to look like that. okay, with the characteristic of the radius here, okay, that's R. All right. So according to AISC, all right, they call this width BF. I don't remember how TIS call it, but it's not BF. But it's the funny thing is this. We use AISC spec or EIT to calculate for calculation. But we use TIS for manufacturing. And you know, the steel company that manufactures the steel structure, they are obliged to show the information based on TIS. So when you look at their catalog, they're not going to call it like this. But when you look at the specification to try to use the guideline for your calculation, they use these nomenclature. So I'm sticking with that one, and I will talk you through the tables that I give you as well, so that you know how we would handle this with the nomenclature based on the IC. That's better. Okay. Anyway, so that's BF. This thickness, it's the thickness of the flange, so they call it TF. TIS, they call it T1. I remember that one. Okay. This is, of course, the depth of your H shape, so it's called D. Here is TW, thickness of the web, right? Very easy to remember. Okay. So now there is another thing that you need to know. Okay. When we try to connect this H shape together through the web, the available space that you have to work with is, of course, the distance between the fillets. Okay. And so they call this distance between the fillets should be equal anyway. This is T. So basically you can say T is equal to the depth minus twice of TF plus R, right? Now in the US, of course, in the AIC spec, that is, this TF plus R, they call it K. Okay, they have more freedom in manufacturing than in Thailand. So in the US, they have, sometimes they have the section where the fillet is not a quarter circle like this. It can be a parabolic shape or stuff like that. So they have to call this K because there are variations of these values. But in this country, everything has to be manufactured according to TIS. Therefore, we can safely say that you have only one kind of a variation for K that is equal to TF plus R. Okay? And T becomes the distance that you have to work with the connection that you put at the web. So let's take a look at the steel table that I have given you. Okay? Now, because this is the table that contains all the necessary engineering section properties for your members. I remember that I mentioned earlier that all the design, all the steel catalog available in the country, the company is only obliged to provide information that TIS asks, and that is simply just the dimensional properties. Okay, you don't have much more than that. And therefore, I have created the this table you know, in collaboration with SYS as well. So you must, you can be sure that, you know, all the numbers here are correct, and you can hold on to this table for the rest of your life, because I think they plan to print them out somehow. Just the funny thing is that they say the promotion department is very busy, so they don't have time to print this out. Anyway, but students in my class, you should have them. Okay, so you can look and you see that. Okay, this is the nominal size, the depth and the width. You know, but the nominal size means that sometimes the depth is not really 100 millimeters and the width is not 50 millimeters. You have to check the real size here. Here's the width. The width of the flange, so it's 50 here, and the depth is 100 meters. But look at this nominal, 200 by 100. You know, for this one, this is the weight per length. For this weight, you have the width that is not 100, it's 99, and then the depth here is 198. Use the actual size here in calculation. Don't use the nominal size. Okay, use the actual size in your calculation. Okay, now so and you have the width, the thickness of the web, you have the thickness of the flange, you have the K value here. The catalog will not have it, but we do. K, which is equal to T flange plus the radius. You have the T, the space available for the connection, and then you have some other stuff which we will go through in the future. Okay, and we also have more in some other tables as well. Okay, so all the sections here with the torsional properties and so, which we will go through in the future. Is there any question on this? Okay, you're not gonna respond to me anyway today. So before I forget, in general, in the US, when they describe the section, they begins with the depth like this, W12, like it's 12 inches deep, multiplied by the weight per length, it's pound per foot. That's for the US. In Thailand, we tend to go for something like H200 by 100. We can, you know, say the weight like this, but it's not really popular. They want to make sure that you get everything correct. So it's 200 by 100. You probably have to state the T web and then the TF. So this becomes something like 5.58 multiplied by 5.5 by 8 by 20.9 kilogram per meter. So this is how they would like to describe the section on the drawings in our country. Okay, and the next thing that you should know is just to call this by the correct name. You can call this Y flange, or you can call this an H shape, because it has a shape of an inverted H. Okay. Sometimes you're gonna hear some people call this IBeam or I shape. Now keep in mind that because this is built on the hot roll process, so we call it the hot roll shape. And for the hot roll I shape, it's not like this. If you talk about an I-beam or an I-shape beam, for the hot roll, it's something like this. This is I-beam. So I'm trying to draw it properly. You see that now that if it is I-beam, I can say I-beam, because, you know, there is a word I-shaped beam, but if it's built up, you have to understand that it's not like this. But anyway, I-beam, this flange is tapered, you see. The slope is there, so the thickness is not constant. So when you refer to as a hot roll I-beam, you are referring to this one. So you don't go around and say, I want an I-beam, and you know, say I-beam in this so and so, when you mean H shape or H beam. Okay, because there are I-beam sections available for hot roll as well. And they have their usage, their purposes. Generally, they use it for rails and you know, crane stuff, but they don't use it for typical structural purposes. Okay, so call them by the correct names. Is there any question? Hello? There isn't. Okay, so predominantly in this class, we're going to use this one. Okay, and from time to time, this is also another popular section, the channel. Okay, so it's just, you know, C shape on the channel. Okay? Pretty similar to the HB. Okay, and you know, this used to be quite a popular section, but not that much anymore because it's rather expensive. The T section, T section is made by cutting the H section in half. All right, so you have two T's coming out of the edge. So that means in order to create a T, you must cut an edge. It used to be very popular in for use for the top and bottom chord of the truss because it's very easy to construct and so, but it's kind of expensive and maybe so the popularity decreases. Okay, you have the angle like that. Okay, and now this is another popular sections that we will use for the truss members. Okay, because it's a closed shape and therefore it doesn't collect dust, and it turns out to be quite beautiful for architects, and you can bend them in any curves that you want. It is very pleasing in the eyes, so they become very popular. But one thing that you must be aware of this section is that they are most of the time, if not all the time, they are made of another material. They are made of material called TIS 107, which doesn't have Fy equal to SS 400. And many students will make mistakes like this, which is very, very sad. And I have to be very, very mean because it's a basic of your design criteria. You must get the material properties of your, say, construction materials right from the beginning. Or else, you know, let's say if the difference is huge, you're going to cause a lot of, say, damage for yourself, for your community, and so on. So I don't remember the FU, but TIS here, FY is like 2400. There are numbers available in the table, which I will post later. But keep in mind, keep this in mind. Okay, and the way they describe the section is, you know, with the dimension, and then that's the thickness. See, that's the thickness. Okay, not the weight. All right. Generally, it's pretty thin. That's 3 millimeters we're talking about. Okay. Now, the next stuff that we need to understand is that according to the law, when you use a steel structure, you need to provide the fire protection. Now, the fire protection is a major struggle in this country because of the incident called the Kada factory a long time ago. A lot of workers died because the truss collapsed. But there was no fire protection for the truss at all. It was a very, very long time ago when I was very, very young. And the law coming afterward, it was very, very strict. So it becomes very difficult. Not impossible, but difficult in terms of it makes the fire protection very expensive. I'm not going to go through details here, but this stuff you need to understand a few things, and when you can give a proper maybe advice to architects as well. So you would know that there are two ways to handle the fire protection. The first one is active system. The next is passive. But the active system, it's got to be active, right? So it would try to prevent the fire to reach the structure. So the active system is like the fire alarm or the sprinkler system. It's a sprinkler, not sprinkler. Okay. So try to pronounce the word properly, and if you run into someone who doesn't pronounce properly, you may choose to inform that someone, hey man, you suck. No, not like that. Hey man, you don't get it right. But if you notice that he or she cannot pronounce sprinkler, you may as well let it go. Okay. Anyway, so passive system would be to try to protect the structure when the fire comes. Oops, hang on 1 second. You know what?
Excuse me, you unmute yourself. Don't forget to unmute.
Thanks a lot. You know what happened? I forgot to turn off the fire. So I'm heating the food. So talking about the fire protection, right? Anyway, yeah, okay. So the second one is the passive. So we put the paint on the structure to try to give it a fireproof. Or you can put the what we call the cementitious material like this. It looks like this. You see, and cementitious material is something that architects don't like very much because they don't look beautiful, do they? Anyway, you should know that if you require the fire protection is given in terms of the hours that your structure can withstand the fire. It's called the fire rate. It's 1 hour, 2 hours, 3 hours. You can always put paint, according to the number of hours that you need, but it's going to cost a lot of money. For example, the 5-hour protection, you can put the very, very thick paint or very thick cementitious material to achieve that, but it's going to cost a lot. So that's why, yeah, because of that very, very strict law, sometimes using a steel structure can be costly because of this. And many folks are trying very hard to overcome, to force this law to be changed. And insofar, I think in the last year, they have been very successful. And at least that should be the major, I cannot say major, maybe hopefully, the overhaul of the fire protection law. Okay. See, so that's about it. You can read more about the stuff that they use in here, or it's for cementitious or active stuff and passive. So that's a cementitious. You see, put this on the roof. That doesn't look very beautiful at all. Let's say if that's the roof of your bedroom, you wouldn't be happy, would you? Anyway, that's it. Now let us talk a little bit about the structural system for the steel. I should hope that you guys are okay with this because you've had the structural analysis with me. But anyway, because the structural analysis number 2 is taken with this course, so I think it's a parallel study, which should, in a way, good for you. Anyway, this you already know. There are two kinds of forces on the structure when we talk about the type of force, right? Based on the direction. First is gravity. You must know it's a force caused by gravity. So we know it's a dead load and live load, and the direction is this one. Right? The downward force. Can you have the upward force? Yeah, sometimes when you're dealing with groundwater and the pressure, upward pressure from the ground, but unlikely for the steel structure, which is the infrastructure on top. Okay, so that's a vertical load, and then the horizontal load, which come from wind and earthquake here. Okay, so we use the beam floor system to take care of the gravity, but when you have the lateral load, the beam doesn't help, right? So we need to plan the system to withstand the lateral load or the lateral force. And there are many available ways to deal with it. You can brace your structure like this with many ways to brace. When you brace the structure, you're going to have what we call the brace frame. That's going to help a great deal in, dealing with the lateral load. If you cannot brace it, because you can see if you brace, you lose the space like this. You cannot use the space in between. So sometimes you cannot brace that. You're going to have to be content to use the frame system. Okay. Frame like that. Now, when you brace, it means that you have a system of a truss. So that means when you have a truss, you can have pin joint. But when you cannot have a frame, you must be content with the, when you don't have the brace, when you don't have the brace, you must be content to have the rigid frame system, meaning that this time you're going to have to make your joints rigid to form the frame. That's why we need to learn about the frame in structural analysis number 1 and number 2, because there are no two ways about it. As soon as you have to deal with the lateral load, you have to have the framing system. And generally in steel structure, there are either the brace frame like number 1 here, or number 2, the rigid frame. The shear wall here is the concrete stuff, so I'm not going to mention that. Okay, yeah, it's another system that you can use to resist the lateral load as well, but it's a concrete stuff. We need to have that, and then we're back on the gravity load system. I hopefully can go over this quickly. Gravity load system, as the name suggests, we have to have the system to deal with the gravity load. So generally, it's a floor beam system. When you have the beam like here, this beam will carry the floor, and this time this is the concrete slab, and you can see that the loading system is gonna be exactly like what we have in the structural analysis, right? And this is the direction of your slab. Half of the load goes with the beam here, the purple one, and another half will go to, say, the blue one here. And the floor system that we use here is hollow core concrete slab. This is very popular in this country. Or you can, and sometimes, to try to reduce that, you can put the floor on this secondary beam, right? And your floor is going to be in this direction, maybe. So this becomes the secondary beam. Or filler beam. And they are in turn going to be carried by this primary beam. Or girder. Just 1 second. Okay, sorry about that. So that's basically the system for gravity load. Okay, and now you can move on. Now another floor system that you can use is called the steel deck, the metal deck. Okay, and the very best way to do it is just to make the composite construction out of it. Make this a composite structure, just like what you had in the mechanics of materials class. Okay, we're gonna put this metal deck on top of the beam, connect the metal deck to the beam by using the shear connectors. Okay, and then pour the concrete on top of it. And this shear connector is going to take care of the shear flow to make them act together as the composite structure, which is a very, very strong structure, because generally when you have a simple beam, you know that the compression is on top and tension is at the bottom, right, for a simple beam. So when you have that, it means that you use concrete to take care of compression and you use steel to take care of tension. So it's a very good, it's a very strong system, but you need to make sure that they work together by connecting them with this shear stud or shear connector. Okay. So that's so many pictures about them. This is how it's done. Okay, that's a metal deck, and then the shear stud, and then you know, after installing everything, and this is the wire mesh to prevent the crack and so on. And see, everything can be done by one person with the small equipment like that, and very, really quickly as well. So that's it. Okay, that's what a shear stud look like. Okay. Called shear connector. So they just have the equipment to weld it to the metal deck very, very quickly. Yeah, that's how it looks like. And the thing is, this is a very, very popular construction abroad. It's like especially the country with steel raw material in abundance, like in the US and China and in Europe and so on. So because it's the steel by itself is very strong, and you know, it requires only one person to do it during the erection. So it's very, very quick. And let's say, what am I going to say? Yeah, strong and quick. That's just about it. Now, what I wanted to say was that it may not be as popular in this country because of the price of steel. We don't have a lot of steel as a raw material, so we have to import. And another thing is that the price of the shear connector here is still pretty expensive. So sometimes not very popular, but I think it's becoming more and more. One thing is that you cannot deny the fact that steel is much more environmental friendly, especially during the construction, and it's way, way, way quicker. So one thing I cannot understand is that they always build the SkyTrain and everything by using concrete. It takes like years to complete the project, right? 3 or 4 years, because you have to cast concrete. While steel, you can reduce that time at least 50% or more. And the foundation and everything will be smaller as well. And yet they keep using concrete. And, you know, it's very dirty. You know, you can look at the environment, it takes a very long time, cause a huge traffic jam. One thing that I do, but Thai government doesn't care about is time as a resource. So you can see that many sectors, they burn time just for fun. Okay, anyway, this is still design class. Let's go astray. So, okay, that's a vertical load system or the gravity load. So you need to have the lateral load system, which you will study along in the structural analysis. Okay, so this is the first one. You can notice that here, you have the brace. See? So it's like you put a truss in the building. That becomes a huge truss there, right? This system is very, very, very strong because there is no shape stronger than a triangle. When you can create a truss, it means you can create a series of triangles put together. Right? So it's a very, very strong system. Anyway, when you cannot have that because you need space to work in the building, you need to have the framing system instead. So here is the frame, there is the column, then there's a beam. So if you have a system like that, you must know that this has to be the rigid joint. Okay. All right. So one thing that you should know is that if you have a typical framing system like this, now this needs a proper explanation, right? So because it's very important. So let's say if I give you the frame in the factory, okay, like this. Generally, if you have the support as a hinge, and if you connect this part of the beam, so to speak, to the column by using a hinge, what's going to happen, folks? Come on, what's going to happen? How many?
It will be rotate. Right.
Pardon me? Navarit, say again, please.
It will be rotate.
I think you probably get it right, but you use the wrong word. But anyway, how many reactions do we have? 4, right? So how many degree of redundancy do we have?
1.
1 degree of redundancy. Very good. So we put 2 hinges there. What's going to happen? So now degree of redundancy is -1, which means the structure is unstable. This is fatal. It's a crime because it's going to collapse. Okay. So if you have a situation like this, because generally in the factory, this is what we do. Okay. If you give, because you are engineers, so what you do is that you will analyze structure and design structure and then give the details of construction so that the structure that people are going to construct will behave exactly the way you want it to. So when you design the structure, say here, if you want it to behave like a hinge, you must know how to give the details so that it behaves like a hinge. But when, which is typical because a hinge is a lot easier to give the details and people do that. But when you design, when you give details here as a hinge, this cannot be designed as a hinge. Otherwise, the frame will become unstable. So here, just like this picture, it will become unstable. So if you are going to have a hinge at the support, this one will have to be designed as a fixed support so that this system is stable. You also have a choice. And remember, this is very, very important because it's a basic structure. It's like the frame, truss frame in the factory, the cable frame in the factory. If you turn this into the fixed support, that can be a hinge. Now your system is stable. But again, as I say, you as an engineer, if you design the structure in such a way, you must know how to make details so that this behaves like a fix. And generally it's really costly and it's kind of difficult. And if you design this as a fix, that means the moment will travel to your foundation as well. And you must design your foundation to undertake the moment, which generally people don't like to do, you know. But the next thing is this. If you have this system, look at the column. The column becomes a cantilever, right? So you must be able to design the column according to this as well. Remember that Ajahn Chulapot may have mentioned, I think he must have mentioned about the K in the design of the long column. And when the support condition changes like this, you have to account for that. Okay, so one viable option is to use this, you know, the hinge here, but the fixed joint. So it's basically a typical frame with hinge foundation. Okay, so that is the system that you need to understand that you must provide for your building. Okay, so that's what it looks like, the moment frame. That's another moment frame. Can you see how stiff they look? Okay, so that becomes a moment frame because we have the rigid joint. Okay, and when you have that, you see how important that is to have the 12 understanding of the behavior of the frame. You have the moment diagram that looks like that. Okay, we'll get to that later in the structural analysis #2 class. So just let you know. Okay, and when you have a brace frame, it can be just one brace here. That's a bracing in your system. You don't have to have the brace for every bay, you know, just one bay that will be enough. So now you already have the brace frame. Okay, it helps a lot. This is way better than, you know, having the moment frame throughout because of the triangle shape. Okay, and there's so many ways that you can brace the structure, you know, and it has its advantages and disadvantages according to the force you have to deal with, and so and so. Okay, that's the examples of how the brace frame look like. You know, if you are lucky, you can put more than one bay of brace there. And notice one thing, you need, this is what we call the gusset plate. The reason that we need to have a gusset plate is that we as engineers want to make sure that the centroid or the center line of the members will meet. So that you can maintain the concept of the truss, right? The center line of the braces will meet the center line of the main member like that. So basically you can claim to have the truss system. If they don't meet, it means that you're going to have the brace that looks like that, right? That part will have moment, and the analysis will be quite complicated, but that's not a problem. But it will have to handle the, you know, forces from the truss system and also the additional moment because of this, what we call the eccentricity. Okay, because the centroids do not meet. Okay, there's more the same. Yeah, same thing, same thing, same thing. Okay, so let's take a little bit of a look here, and let's hope that I can finish this before we take another break. Okay, this is the typical look at the frame that I just drew a few moments earlier. You can see that this is where the frame is, right? And generally, this frame will have to handle the lateral load from both directions. And one direction is this, coming in to the side. And when the load coming into the side like that, this is the frame that will have to tackle the load without any help. Okay, so you see, this frame will have to be very, very strong in this direction because there's no help. It's just one frame against the load. But when the wind or the lateral load comes in this direction, okay, just go along the length of the building. You see now you have a series of this frame put together. So in side view, you see, okay, I have a lot of frames now. So and so. So generally, in this direction, the frame is pretty strong. But not only that, naturally, this, you know, this here is part of the wall, right? So that means you're free to put the bracing on it as well. So not only that they're pretty strong because they have so many columns, you can put a brace on them. So that means on this direction, you have to have a strong frame. So that's why you should put the strong axis of your member against this direction, against the load in this direction. Okay, so that is the system integrity for you. Okay, the two directions of the lateral load. You need to make sure that the standalone frame here is strong enough to withstand the lateral load coming in this direction. And then this, you know, things are taken pretty much care of itself because not only that you have so many frames, but also you can put braces on. Okay, so you can put the weak direction of the structure in this. Okay, we still have like 3 minutes left, so that's a system for you. Okay, this is how you can. It's just nothing. You can design the layout where you want to put the frames on to resist the lateral load and so and so. Okay, then another one is the truss now. Okay, we're gonna get to that because the least that you should be able to do out of this class is to design a simple truss system. Okay, and you should know that you guys have created a truss with Ajahn Julapot? Did you have the class, or what was it canceled because of COVID? Hello?
Yes, it canceled.
Oh, that's unfortunately. Anyway, before I talk about the truss, let's put a break here. Okay. Let's say we have 2 minutes, so let's say, yeah. Let's talk about this for a minute. This is called cast let it be. You know, it is created by cutting the edge shape like this. And weld them back together. You just lift them and weld them back together at this location so that the depth is increased. Okay, so it's very, very, say, efficient way to create the section. It's called castellated because it looks like a part of the castle. Castellated beam. Sometimes they cut it in circles, or it's called or circular beam. It's cut in circle. The good thing is that you increase the section property very efficiently, but you have to consider the fact that you're going to have to pay a little more for cutting process and welding process as well. And one additional thing is that it's going to have a special failure way to fail. You must check. Okay. Is there any question? Okay. Let me stop the record.